There's a planet 40 light years from Earth that scientists have started calling, in peer-reviewed journals, potentially more habitable than the one you're standing on right now. Not a gas giant, not a lava world, not a planet that has water somewhere deep underground in some technically liquid but freezing subsurface ocean that nothing meaningful could survive in. A rocky, Earth-sized world sitting in the exact right distance from its star to have liquid water on the surface. A planet that has been observed transiting its star over 1,000 times. A planet that the James Webb Space Telescope has already begun to characterize. A planet that, by several measurable criteria, scores higher than Earth on the indices scientists use to evaluate how well a world can support life. The planet is TRAPPIST-1e, and the claim that it might be more habitable than Earth is a serious scientific argument made by serious scientists in rigorous literature. Not because it looks like a postcard version of what a habitable planet should be, but because of a concept that has quietly reshaped how astrobiologists think about life in the universe over the last decade. That concept is superhabitability. The idea that Earth, as remarkable as it is not necessarily the best possible planet for life. That there are configurations of rocky worlds around stable stars that are, in specific and measurable ways, more conducive to the development and persistence of complex life than the planet that produced us. And that one of those configurations may be sitting in the TRAPPIST-1 system, 40 light years away, waiting for us to look at it properly. This video is going to do 3 things. It's going to explain what TRAPPIST-1e actually is, the real measurements, the models, the genuine uncertainties. It's going to explain the superhabitability framework and why the comparison with Earth is more than hype. And it's going to explain what we still don't know and what the James Webb Space Telescope is in the process of finding out right now. Because in this case, the difference between what we know and what we suspect is the most important distinction in the entire story. We're going to start with the star, because everything about TRAPPIST-1e, everything unusual, everything potentially remarkable, is a direct consequence of the nature of its host star. And that star is, by any standard, one of the strangest and most consequential objects in the history of exoplanet science. Chapter 1: The Star That Will Outlive the Universe. TRAPPIST-1 is a red dwarf, not the relatively familiar kind of red dwarf, the K-class or early M-class stars that appear in lists of potentially habitable stellar neighborhoods, but an ultra-cool dwarf, classified as M8, sitting at the very bottom of the main sequence. Below it on the mass scale are brown dwarfs, objects that couldn't quite accumulate enough mass to ignite stable hydrogen fusion in their cores, and now glow dimly from gravitational contraction heat alone. TRAPPIST-1 made it over that threshold, barely. Its mass is about 8% of the Sun's. Its radius is about 11.5% of the Sun's, roughly the size of Jupiter. It emits about 0.05% of the Sun's total luminosity. Its surface temperature is approximately 2,566 Kelvin compared to the Sun's 5,778 Kelvin. It glows a deep, murky brownish red, and it's so faint, magnitude 18.8, that it's completely invisible to the naked eye from Earth. even though it's only 40.66 light years away, which is cosmically close. If you pointed a decent amateur telescope at the right patch of sky in Aquarius and didn't know exactly where to look, you'd miss it entirely. None of this sounds immediately compelling for habitability. A dim, cool, tiny star doesn't obviously sound like the best host for a world where life might thrive. But TRAPPIST-1 has a property that, once you understand its implications, changes the entire calculation. It is almost unimaginably old relative to the timescales of stellar evolution that we're used to thinking about. And it will remain almost identical to what it is now for a period of time that makes the current age of the universe look like a rounding error. The main sequence lifetime of a star, the period during which it burns hydrogen stably in its core, scales inversely with its luminosity. Massive, bright stars burn through their fuel quickly. Our sun will exhaust its hydrogen in a total of about 10 billion years, roughly half of which has elapsed already. A star twice the sun's mass might last only 2 billion years before expanding into a giant. And TRAPPIST-1, burning its modest fuel supply at a glacially slow rate, its main sequence lifetime is estimated at approximately 10 trillion years. That is roughly 700 times longer than the current age of the universe. The universe is 13.8 billion years old. TRAPPIST-1 will still be burning at approximately its current luminosity for another 9.99 trillion years after today. To appreciate what this means for habitability, consider the timeline of life on Earth. Life appeared relatively quickly, probably within the first 300 to 500 million years after Earth's surface cooled enough to allow liquid water. But the subsequent journey from early microbial life to complex multicellular organisms took about 3 billion more years. The emergence of animals happened around 600 million years ago. Technological intelligence has been present for a few 100,000 years. The entire known arc of complex life on Earth has played out in something like 600 million years, about 6% of the Sun's total main sequence lifetime. On a TRAPPIST-1 planet, the equivalent 6% of the star's main sequence lifetime would be 600 billion years. Any biosphere that gets started on a TRAPPIST-1 world doesn't have billions of years of habitable time ahead of it. It has trillions. The evolutionary window is not constrained by stellar lifespan in any meaningful sense. If life can get started and maintain itself through the early challenges, and there are real early challenges we'll discuss, it has essentially forever to grow in complexity. Before accepting this longevity argument uncritically, it needs one important qualification. M-dwarf stars like TRAPPIST-1 are not uniformly well behaved over their trillion-year lifespans. Young M-dwarfs are magnetically hyperactive. They flare frequently and intensely, emitting bursts of X-ray and ultraviolet radiation that can be orders of magnitude brighter than the stellar quiescent emission. TRAPPIST-1 itself flares dozens of times per day, with occasional superflares that briefly increase the star's X-ray output by a factor of hundreds or thousands. These flares are a real habitability challenge, and we'll examine them in detail in later chapters. The relevant point for the longevity argument is the distinction between the early active phase and the settled middle age period. In TRAPPIST-1's case, the intense magnetic activity phase was concentrated in roughly the first 1 to 2 billion years of the star's life. After that, as with all M dwarfs, the activity progressively declined. TRAPPIST-1 today, at an estimated age of 5 to 10 billion years, is in a settled, relatively quiet phase. It still flares, M dwarfs never fully stop, but the frequency and intensity of large flares has declined substantially from the early period. The next 10 trillion years of TRAPPIST-1's life will be characterized by this settled, moderate activity state. So the longevity argument is not 10 trillion years of flares. It is a potentially rough first 1 to 2 billion years, followed by 9.998 trillion years of stable, moderate conditions. The habitability question is whether a planet can survive the rough early phase with enough atmospheric and oceanic inventory to be habitable during the long settled phase that follows. This is the first and most fundamental reason TRAPPIST-1 matters. It's not primarily about what the star is right now. It's about what the star will still be in conditions almost identical to current conditions when the sun has been dead for 1 trillion years. The system sits in the constellation Aquarius, 40.66 light-years away, close enough that its planetary system is observable in useful detail with current technology, and close enough that future missions involving direct imaging or atmospheric characterization at high resolution are within the bounds of conceivable engineering. Chapter 2: 7 Worlds. How the system was found. The discovery story of the TRAPPIST-1 system is worth telling in full because it explains why we know as much as we do about these planets, and because the method used to find them is the same method now being used by JWST to probe their atmospheres. The instrument that started everything was not a famous space telescope. It was a modest, purpose-built 60-centimeter, ground-based telescope at the La Silla Observatory in Chile, operated by a team from the University of Liège in Belgium, led by astronomer Michael Gillen. The telescope was called TRAPPIST, for Transiting Planets and Planetesimals Small Telescope, and its very specific mission was to stare at ultra-cool dwarf stars and look for transits. A transit is a geometrical accident. When a planet's orbit is aligned with our line of sight, the planet passes across the face of its star as seen from Earth, briefly blocking a small fraction of the star's light. For a sun-like star, an Earth-sized planet produces a transit dimming of about 0.008%, a signal so small that detecting it reliably requires space telescope quality photometry over many orbits. But for an ultra-cool dwarf like TRAPPIST-1, where the star itself is barely larger than Jupiter, the same Earth-sized planet produces a transit dimming of about 0.5 to 1%. That's a factor of 60 to 100 easier to detect. Gillen's team designed their program specifically to exploit this, using small, cost-effective telescopes to survey the dimmest stars that standard transit surveys had largely ignored. The first announcement came in May 2016. Gillen's team reported 3 planets around TRAPPIST-1, designated B, C, and D, with orbital periods short enough to be confirmed from just a few months of ground-based monitoring. 2 of them were already suspected to be in or near the habitable zone. The paper triggered immediate worldwide follow-up. The second announcement, in February 2017, was the one that entered general scientific consciousness. Using 20 continuous days of monitoring from NASA's Spitzer Space Telescope, which, in infrared, was well suited to observing the dim red star, combined with data from multiple ground observatories, Gillen's expanded team resolved the full architecture of the system. 7 planets, designated B through H, orbital periods of 1.5, 1, 2.42, 4.05, 6.10, 9.2, 1, 12.35, and 18.77 Earth days. All 7 rocky, all 7 Earth-sized, 3 of them, E, F, and G, squarely in the habitable zone. The simultaneous discovery of 7 rocky planets around a single star was unprecedented. Nothing in the prior history of exoplanet science had produced a comparable result. And immediately, a key observational fact made the system more scientifically tractable than it might otherwise have been. All 7 planets transit the star from Earth's perspective. In a randomly oriented system, the probability of a single planet transiting is a few percent. 7 planets all transiting simultaneously requires a nearly edge-on orbital configuration relative to Earth. And while the geometry of the system makes this more likely than pure chance, it is still a remarkable alignment that allows all 7 planets to be studied with the same transit-based techniques. Here is the detail that made the initial measurements more precise than almost any other planetary system ever studied: transit timing variations. Because all 7 planets are close to each other in a compact resonant architecture, they gravitationally tug on each other as they orbit. These tugs cause tiny deviations from perfectly regular transit timing. A planet arrives at its predicted transit time a few seconds early or late, depending on where its neighbors are in their orbits. These deviations encode information about the mass of each planet. By fitting models to the transit timing variations of all 7 planets simultaneously, the team extracted mass estimates for every planet in the system from photometry alone. No spectroscopy required. For TRAPPIST-1e specifically, the measurements converged on a mass of approximately 0.692 Earth masses and a radius of approximately 0.910 Earth radii. Combining these gives a bulk density of approximately 5.65 grams per cubic centimeter, slightly denser than Earth's 5.51 grams per cubic centimeter by central estimate, though the measurement uncertainties are substantial. Interior modeling consistent with this density suggests a rocky planet with a possible water mass fraction ranging from near zero to potentially several percent by mass. Earth's water fraction, for comparison, is about 0.02%. Even a 1% water mass fraction for TRAPPIST-1e would mean 50 times more water than Earth. 5% would mean 250 times more. These aren't oceans. They're potential global hydrospheres. The orbital period of TRAPPIST-1e is 6.10 Earth days. Its orbital semi-major axis is 0.02925 astronomical units, about 4.4 million kilometers from its star. It receives a stellar flux of approximately 0.646 times Earth's solar flux. This positions it within the classical habitable zone, the range of orbital distances where surface liquid water is theoretically sustainable using multiple different habitable zone models. In the years since 2017, the mass and radius measurements for the TRAPPIST-1 planets have been refined through additional transit timing variation analyses and high-precision photometric campaigns. The current best fit values for TRAPPIST-1e place it firmly in the category of rocky, potentially ocean-bearing worlds. It is not a gas ball. It is not a lava world. It is a rocky planet, roughly Earth-sized, receiving roughly 2/3 of Earth's sunlight, at the right orbital distance to potentially maintain liquid water on its surface. That's the baseline. Everything else builds from there. Chapter 3. What superhabitability actually means, and why. Earth isn't the top score. Before you can evaluate whether TRAPPIST-1e is more habitable than Earth, you need to understand what more habitable means scientifically. Because if your definition of habitable is looks like Earth, then TRAPPIST-1e doesn't win, and neither does any other planet, because by definition, Earth is the most Earth-like planet. But that's a circular definition that doesn't tell you anything interesting about how life might flourish elsewhere. The scientific framework that breaks this circularity is superhabitability, formalized in a 2020 paper in the journal Astrobiology by René Heller of the Max Planck Institute for Solar System Research and John Armstrong of Weber State University. Their argument starts from a deceptively simple observation. We have exactly one example of a habitable planet, and we have no reason to believe it represents the maximum on any biological productivity scale. Earth might be average. Earth might be below average. We simply don't know because we've never been able to compare it to anything. Heller and Armstrong set out to determine, from physical and biological first principles, what a planet would look like if it were optimized for life, not just barely capable of it, but maximally productive and stable over the longest possible timescales. They identified several key parameters. Let's go through them carefully, because this is the framework you need to evaluate TRAPPIST-1e's case. The first parameter is the host star. The ideal host in the superhabitability framework is not a G-dwarf like our Sun. It's a K-dwarf, a slightly cooler, slightly less massive orange star. K-dwarfs have several advantages. They're less magnetically active than the Sun in middle age, meaning lower ultraviolet and X-ray fluxes that can damage atmospheric chemistry and surface life. Their habitable zones, while closer than the Sun's, are not so close that tidal locking dominates. And critically, their main sequence lifetimes range from 15 to 45 billion years, longer than the Sun's 10 billion years by a substantial margin, providing a much larger window for biological complexity to develop and accumulate. The deeper argument for K-dwarfs is about timing. Complex multicellular life on Earth took roughly 3.5 billion years after life's origin to emerge. That's a long time. And a G-dwarf star like the Sun only has about 10 billion years total on the main sequence. Any habitable zone planet around a G-dwarf only has about 5 to 6 billion years of future stable conditions remaining at any given point, which constrains how much more evolutionary time is available. A K-dwarf planet has potentially 20 to 40 billion years remaining. And an M-dwarf like TRAPPIST-1 has, as noted, essentially unlimited time, complicated by its early activity phase, which is the key caveat we'll get to. The second parameter is planetary mass. Heller and Armstrong identified a mass range of about 1.0 to to 1.5 Earth masses as superhabitable. A slightly more massive planet retains its atmosphere more effectively because of stronger surface gravity. It generates more internal radiogenic heat from a proportionally larger inventory of radioactive isotopes, sustaining geological activity for longer. More geological activity means more efficient recycling of the carbon silicate cycle, the long-term climate thermostat that has kept Earth habitable for billions of years despite the sun's slowly increasing luminosity. More geological activity also means more volcanic island and ridge formation, increasing the area of shallow coastal habitat, which is biologically the most productive environment on Earth. A more massive rocky planet is also more likely to maintain plate tectonics for longer. There's a debate in the geophysics community about exactly what conditions are required for plate tectonics to operate, but the broad consensus is that a more massive, hotter interior is more conducive to it. Plate tectonics on Earth provides the carbon cycle, diverse geological environments, and chemical gradients that may have been essential to the origin and persistence of complex life. A planet that sustains it robustly for 5 billion years, instead of Earth's potentially punctuated history, gets a higher score on this metric. The third parameter is water, not a little more water than Earth, meaningfully more. Earth's oceans are, despite appearances, quite thin relative to the planet's size. If you compressed Earth's total water inventory into a spherical shell, it would be less than 3 kilometers thick across the entire planet. The oceans are shallow. Most of the deep ocean floor, below about 200 meters, is biologically sparse, cold, dark, nutrient limited. It's the shallow coastal zones, the continental shelves, the warm tropical seas where biology explodes into richness. Coral reefs occupy less than 0.1% of the ocean floor, but contain about 25% of all marine species. Shallow, warm water is the engine of marine biodiversity on Earth. A superhabitable world would have more water distributed more uniformly, creating a larger area of shallow, productive ocean. Think less deep abyssal ocean and more warm, shallow, sunlit water covering most of the surface. Biological productivity in such an environment would be higher almost everywhere on the planet, not concentrated in the thin ribbon of coastal shallows as it is on Earth. The fourth parameter is mean surface temperature. Earth's average surface temperature is about 15 degrees Celsius. Life exists across a far wider range, from -20 in Antarctic ice to over 120 in hydrothermal vents. But biodiversity peaks in warm tropical and subtropical zones, roughly 25 to 30 degrees Celsius. A superhabitable world with a mean surface temperature of 25 to 30 degrees, warmer than Earth but not lethally so, would have a larger fraction of its surface in the peak biodiversity temperature band. More warm area means more productive habitat across the board. The fifth parameter is age. An older biosphere has had more time for evolution to fill niches, develop complexity, and produce the kind of multi-level ecological structure, predators, prey, decomposers, symbiotes, that characterizes mature ecosystems on Earth. A planet with the same physical characteristics as Earth, but 5 billion years older, would be expected, if it had maintained habitable conditions throughout, to have a vastly more complex and diverse biosphere. The qualification is critical. an older planet has also had more time to be disrupted by mass extinctions, host star variability, and geological events. But all else being equal, more evolutionary time is more evolutionary time. Now, how does TRAPPIST-1e score? On stellar type, the story is mixed. TRAPPIST-1 is an M8 dwarf, more extreme than the ideal K dwarf in ways both good and bad. The magnetic activity in youth is worse than a K dwarf. Tidal locking is more likely. But the main sequence longevity is incomparably better. Trillions of years versus the K dwarf's tens of billions. If TRAPPIST-1e can get past the early challenges, and this is the core question, the long-term stability of conditions is unmatched by any other stellar category. On planetary mass, TRAPPIST-1e at 0.692 Earth masses is actually slightly below the superhabitable ideal. A lower mass planet has weaker gravity, less efficient atmosphere retention, and potentially less internal heat. This is a genuine mark against it in the superhabitability framework. However, as we'll explore in Chapter 7, there is a compensating mechanism specific to this system, tidal heating from the orbital resonance, that may substitute for some of the missing radiogenic heat. On water, TRAPPIST-1e almost certainly scores higher than Earth. The density measurements are consistent with a substantially higher water mass fraction. Whether that water is distributed as shallow, productive seas or as a crushing, deep global ocean is the critical question for whether the water richness is a biological advantage or a complication. On surface temperature, the current models span a wide range for TRAPPIST-1e, from fully glaciated to comfortably warm, depending primarily on the atmospheric composition and greenhouse gas inventory. There's no settled answer here yet, but many model configurations produce mean surface temperatures in the range that superhabitability theory predicts as optimal. On age, TRAPPIST-1 is estimated at 5 to 10 billion years old, probably older than the Sun's 4.6 billion years. If the system is at the upper end of that range, and if habitable conditions were established early, TRAPPIST-1e's biosphere has had more evolutionary time than Earth's. The qualifier "if" does real work in that sentence. The overall scorecard: TRAPPIST-1e doesn't sweep the superhabitability criteria, but it hits several of them: water, potential age, extraordinary long-term stellar stability, in ways that Earth doesn't. And the criteria it misses most, stellar type and planetary mass, have specific compensating factors unique to this system. Chapter 4, the habitability zone, where TRAPPIST-1e actually sits. The habitable zone is one of the most used and most misunderstood concepts in exoplanet science. Let's be precise about what it is, what it isn't, and where TRAPPIST-1e falls within it. The habitable zone, also called the Goldilocks zone in popular writing, is defined as the range of orbital distances from a star within which a rocky planet with a specific kind of atmosphere could maintain liquid water on its surface. The specific atmospheric assumption baked into the classical habitable zone definition is a CO2H2ON2 atmosphere, like Earth's, but with variable CO2 content, regulated by the carbonate-silicate cycle. The inner edge of the habitable zone is where the greenhouse effect from water vapor runs away and drives a catastrophic warming that evaporates all surface water, the Venus scenario. The outer edge is where even a maximum CO2 greenhouse atmosphere can no longer keep the surface above freezing, the early Mars scenario. This definition has several important caveats. It is defined for a specific atmospheric assumption. A planet with a different atmospheric composition, more hydrogen, which is a powerful greenhouse gas, or a different mix of greenhouse gases, can be habitable outside this range. The habitable zone is not a hard boundary, but a probabilistic guide to where liquid water is more likely given nominal atmospheric assumptions. And it says nothing about whether a planet actually has an atmosphere, has liquid water, or has life. With that caveat noted, TRAPPIST-1e sits comfortably within the habitable zone by the most widely used habitable zone models. The Koparapu et al. 2013 Habitable Zone Model, the standard reference in the field, places the inner edge of TRAPPIST-1's habitable zone at approximately 0.021 astronomical units, the recent Venus inner limit, and the outer edge at approximately 0.046 astronomical units, the early Mars outer limit. TRAPPIST-1 E orbits at 0.02925 astronomical units, well within this range, closer to the inner edge than the outer, but solidly in the middle third. For comparison within the TRAPPIST-1 system, TRAPPIST-1b at 0.011 astronomical units is clearly inside the habitable zone and certainly too hot. TRAPPIST-1c at 0.016 astronomical units is marginal to hot. TRAPPIST-1d at 0.022 astronomical units is at or near the inner edge. TRAPPIST-1e at 0.029 astronomical units is comfortably inside. TRAPPIST-1f at 0.037 astronomical units is also inside. TRAPPIST-1g at 0.045 astronomical units is near the outer edge. TRAPPIST-1h at 0.063 astronomical units is outside the habitable zone and likely too cold without additional greenhouse warming. So 3 planets, E, T, and G, are simultaneously in the habitable zone, which is itself unprecedented in any known planetary system. Why does TRAPPIST-1e get the most attention of the 3? Several reasons. It's the most Earth-like in terms of the stellar flux it receives. 66% of Earth's compared to TRAPPIST-1f's 38%. It's the planet most analogous to Earth in terms of its energy balance, and so the one for which atmospheric models produce the widest range of plausibly warm scenarios. TRAPPIST-1f is colder, and maintaining liquid surface water there requires a more substantial greenhouse effect. TRAPPIST-1g is near the outer edge and requires aggressive greenhouse warming in most models to avoid freezing entirely. What does receiving 66% of Earth's solar flux actually mean for the planet's surface? A quick energy balance calculation helps anchor the intuition. Earth's equilibrium temperature, the temperature a bare black body at Earth's distance from the sun would reach, is approximately 255 Kelvin, or minus 18 degrees Celsius. Earth's actual mean surface temperature is 288 Kelvin, or about 15 degrees Celsius. The difference of 33 degrees is the greenhouse warming provided by Earth's atmosphere. TRAPPIST-1e, receiving 66% of Earth's solar flux, has an equilibrium temperature of approximately 251 Kelvin, about 4 degrees colder than Earth's bare rock equilibrium, with a greenhouse atmosphere comparable to Earth's, That translates to a mean surface temperature around 10 to 11 degrees Celsius, assuming similar atmospheric composition, with a somewhat stronger greenhouse. More CO2 or more water vapor from a richer ocean. TRAPPIST-1e could reach mean temperatures of 20 to 25 degrees, placing it squarely in the superhabitable temperature optimum. One nuance worth noting: the light TRAPPIST-1e receives from its star is much redder than Earth's sunlight. The star's cool surface temperature means most of its emission is in the near-infrared rather than the visible. This has a specific consequence for surface albedo. Ice and snow are highly reflective at visible wavelengths. They bounce back much of the sunlight hitting them, which on Earth provides a powerful, positive feedback for glaciation. But ice is much less reflective in the near-infrared. A TRAPPIST-1e covered in ice reflects much less of its incoming stellar radiation than a similarly ice-covered Earth would reflect solar radiation. This means TRAPPIST-1e is much more resistant to a runaway ice albedo feedback that could lock it into a permanent frozen state. Its icy surfaces absorb more of the available starlight, warming the planet and counteracting glaciation. This spectral effect is a genuine physically motivated reason why TRAPPIST-1e is more likely to avoid the snowball planet fate than its equilibrium temperature alone would suggest. There's another reason TRAPPIST-1e attracts attention. Its position relative to the 3 other habitable zone planets sets up an interesting comparative study. TRAPPIST-1c, just inside the habitable zone, has now been characterized by JWST as having low enough thermal emission to rule out a thick Venus-like atmosphere. TRAPPIST-1e, further out, receives less radiation and faces less aggressive atmospheric escape. If there is a gradient of atmospheric inventory across the inner TRAPPIST-1 system, with the inner planets stripped and the outer planets retaining atmospheres, then TRAPPIST-1e may sit just at the transition point where atmospheres begin to survive. This is speculative, but not arbitrary. It's grounded in the physics of atmospheric escape, which scales strongly with the stellar radiation flux received. The further a planet is from an active M-dwarf, the less intense the atmospheric escape driving forces. TRAPPIST-1e's position in the habitable zone isn't just about temperature. It may also be the planet that sits at the threshold of atmosphere retention. Chapter 5: Tidal Locking. The thing that sounds like a problem. Almost every popular article about TRAPPIST-1e raises tidal locking as a potential showstopper for habitability, and almost every popular article either overstates the problem or doesn't explain it properly. Let's do both things correctly. Tidal locking is what happens when the tidal forces exerted by a star on a close orbiting planet synchronize the planet's rotation period with its orbital period. It's the same phenomenon that keeps the moon always showing one face to Earth. The moon is tidally locked to Earth. At the orbital distance of TRAPPIST-1e, 4.4 million kilometers from the Yu star, the tidal forces from TRAPPIST-1 are strong enough to have synchronized TRAPPIST-1e's rotation within the first few hundred million years of the system's history, almost certainly. TRAPPIST-1e rotates once every 6.10 days, matching its orbital period. One hemisphere permanently faces the star, the other permanently faces away. The naive habitability concern is obvious: permanent dayside and permanent nightside. The day side would be constantly illuminated and heated. The night side would be in perpetual darkness. Conventional intuition suggests the atmosphere would freeze out on the cold night side and collapse to the surface as solid CO2 or N2 ice, leaving the planet airless and dead. Here is where the intuition breaks down. Multiple independent climate models developed since 2015, using global circulation models originally developed for Earth and modified for tidally locked conditions, run by groups at MIT, University of Washington, Exeter, and other institutions, have consistently found that tidally locked planets with substantial atmospheres don't simply freeze on the night side. They develop powerful, persistent atmospheric circulation patterns that redistribute heat from the day side to the night side efficiently enough to prevent atmospheric collapse. The mechanism is straightforward thermodynamically. If you heat one side of a fluid-filled sphere and cool the other, the fluid flows from the hot side to the cold side. The atmosphere of a tidally locked planet does exactly this. The substellar point, the point directly beneath the star at the center of the day side, is continuously heated and becomes the highest pressure point. Warm air rises there and flows outward toward the terminator, the day-night boundary, and then around to the night side, where it cools and descends. The return flow at lower altitudes carries cool air back from the night side to the day side. The result is a persistent, globe-spanning atmospheric circulation that efficiently moves heat from day side to night side. The efficiency of this heat redistribution depends primarily on the atmospheric mass. A thin atmosphere with low total heat capacity circulates but doesn't redistribute enough heat to prevent night side freezing. A thick atmosphere comparable to or greater than Earth's redistributes heat very efficiently. The threshold for preventing night-side atmospheric collapse in the TRAPPIST 1E-like models is roughly comparable to Earth's atmospheric pressure, approximately 1 bar of surface pressure. Above this threshold, most model runs produce a planet with moderate temperatures across both hemispheres, rather than an extreme day-night dichotomy. The specific temperature patterns on a tidally locked world are interesting. The substellar point is warm, but not as hot as you might expect. Cloud formation at the substellar point is a strong negative feedback in many models, with deep clouds forming there that reflect incoming stellar radiation and prevent extreme heating. The night side is cool but not frozen in most model configurations, with an Earth-like atmospheric mass. The terminator region, the permanent ring of sunrise and sunset encircling the planet, has some of the most stable and moderate temperatures on the surface because it receives oblique, low-angle illumination from the star and sits between the redistributed warmth of the upper night-side atmosphere and the moderate day-side temperatures. This terminator belt, sometimes called the terminator habitability zone, is where the most interesting habitable real estate on TRAPPIST 1E might be located if the planet has liquid water. It's a continuous band running all the way around the planet at the day-night boundary. Perpetual oblique sunlight, moderate temperatures, probably some precipitation where the warm, moist air from the day side meets the cooler night side air. Life in this band wouldn't experience day and night in any conventional sense, but it would have a stable thermal and light environment unlike anything on Earth. There is one more subtlety about tidal locking that is worth addressing. The the possibility that TRAPPIST-1e is not perfectly synchronously rotating, but instead in a higher spin resonance, like Mercury in our solar system. Mercury orbits the Sun 3 times for every 2 rotations, a 3-to-2 spin-orbit resonance, rather than being fully synchronized. Whether TRAPPIST-1e is in synchronous rotation or in a higher resonance depends on its eccentricity and its tidal dissipation properties. Models suggest synchronous rotation is most likely for the current orbital configuration, but a non-synchronous state cannot be definitively ruled out with current observations. A non-synchronous TRAPPIST-1e would experience a slow day-night cycle, rotating relative to the star over a period much longer than its orbital period, still very different from Earth's 24-hour cycle, but removing the extreme, permanent day/night dichotomy entirely. Chapter 6. The Atmosphere. Question: Everything rides on. This everything discussed so far, the habitability zone position, the superhabitability potential, the tidal locking climate models, is predicated on a single assumption: that TRAPPIST-1e has an atmosphere. If it doesn't, none of the rest matters. The surface would be directly exposed to stellar radiation and the stellar wind. The temperature would be determined by bare rock radiative equilibrium at about -35 degrees Celsius, and the planet would be biologically barren. Whether TRAPPIST-1e has an atmosphere is the central unresolved question in the study of this planet, and answering it is the primary scientific mission of the James Webb Space Telescope, as it relates to the TRAPPIST-1 system. But before getting to what JWST has found so far, it's important to understand the forces competing for and against atmosphere retention. The force working against atmosphere retention is atmospheric escape driven by stellar radiation. TRAPPIST-1, like all M-dwarf stars, was significantly more magnetically active in its first billion to 2 billion years of life than it is today. A younger M-dwarf emits elevated levels of extreme ultraviolet and X-ray radiation, EUV and XUV, that heat the upper atmospheres of close-in planets to temperatures where the gas can escape to space. The dominant escape mechanism is photoionization-driven escape, sometimes called hydrodynamic escape or boil-off. The upper atmosphere absorbs EUV photons, the gas heats up, and the heated gas flows outward beyond the planet's gravitational escape velocity. This process is most efficient when the EUV flux is high and the planet's gravity is low, both of which are more true for TRAPPIST-1e than for Earth. Models of atmospheric escape for the TRAPPIST-1 habitable zone planets during the active early phase of the star generally conclude that the planets could have lost substantial atmospheres if the initial volatile inventory was Earth-like. One influential study estimated that TRAPPIST-1e could have lost the equivalent of several Earth ocean masses of water to escape processes during the first 2 billion years of the system's history. This is a sobering finding, but it depends heavily on the initial volatile inventory, which is unknown. Here is the key counterpoint. The density measurements of TRAPPIST-1e are consistent with a water mass fraction much larger than Earth's. If TRAPPIST-1e formed beyond the ice line in the protoplanetary disk and then migrated inward, as the resonant chain orbital architecture strongly suggests it did, it may have formed with 10 to 50 times Earth's total water inventory before any escape processes began. In that scenario, even losing several Earth-ocean masses to atmospheric escape over the active early stellar phase still leaves a substantial water and volatile inventory. The planet starts the habitable phase of the stars, life with a large residual atmosphere and surface water reservoir, not with a stripped crust. The forces working in favor of atmosphere retention include the planet's gravity, any planetary magnetic field, and the ongoing replenishment of volatiles through volcanic outgassing from the interior. TRAPPIST-1E's gravity at 0.692 Earth masses is less than Earth's, somewhat weaker retention. Whether it has a magnetic field depends on its interior, specifically on whether it has a liquid iron core generating a dynamo. This is not observationally constrained for TRAPPIST-1E yet. But the tidal heating from the resonant orbital chain, which may be maintaining an active interior, could in principle also be maintaining a liquid outer core and therefore a magnetic field. The same mechanism that drives Io's extraordinary geological activity, though without the volcanism being so extreme as to be destructive. The outgassing factor is important and often underweighted in popular discussions. Earth continuously replenishes its atmosphere through volcanic activity. CO2, SO2, water vapor, and other gases released by volcanism replace gases lost through various escape and weathering mechanisms. A tidally heated, geologically active TRAPPIST-1E would be outgassing substantially, potentially maintaining an atmospheric composition and pressure in a dynamic steady state between loss at the top and replenishment from below. This doesn't require the initial volatile inventory to have been perfectly preserved through the early active phase. It requires ongoing replenishment to be sufficient to maintain a significant atmosphere under the current, much milder stellar radiation environment. The current TRAPPIST-1, middle-aged reduced activity, is a much gentler radiation environment than the young star was. EUV and XUV fluxes decline substantially as M dwarfs age. By the time a TRAPPIST-1-like star is 5 to 10 billion years old, its atmospheric escape driving force is only a fraction of what it was in the first billion years. An atmosphere that can be maintained in the current environment is not under the same threat as the primordial atmosphere was. The question is whether enough volatiles survived the early phase to create what's there now. Chapter 7, James Webb is already looking. The first results. The James Webb Space Telescope is the most powerful space observatory ever deployed, and a significant fraction of its early observing time has been dedicated to the TRAPPIST-1 system. This is not accidental. The TRAPPIST-1 planets were identified early in the mission planning process as the highest priority targets for rocky planet atmospheric characterization, precisely because the star's small size makes the atmospheric transit signals measurable in principle with JWST's sensitivity. The method JWST uses to probe planetary atmospheres is transmission spectroscopy. When a planet transits its star, a small fraction of the starlight passes through the planet's atmosphere before reaching the telescope. Different molecules in the atmosphere absorb light at different, specific wavelengths. CO2 at 4.3 micrometers, water vapor at 1.4 and 1.9 micrometers, methane at 3.3 micrometers, ozone at 9.6 micrometers. If an atmosphere is present and thick enough, The transit depth is slightly larger at these wavelengths than at wavelengths where no molecular absorption occurs. JWST can measure these tiny wavelength-dependent differences and from them determine what molecules are present in the atmosphere. For the TRAPPIST-1 planets, the first results came from the innermost worlds. TRAPPIST-1b, the hottest planet in the system, was characterized in 2023 using thermal emission measurements. JWST measured the heat emitted directly from the planet's day side as it disappeared behind the star in what's called a secondary eclipse. The result? The dayside temperature of TRAPPIST-1b is approximately 500 Kelvin, higher than what would be expected if a thick atmosphere were redistributing heat from the dayside to the nightside. The data are most consistent with a bare rock dayside with no substantial atmosphere. TRAPPIST-1b, to current observations, appears airless. In 2024, JWST published results for TRAPPIST-1c. The thermal emission from TRAPPIST-1c was found to be lower than TRAPPIST-1b, somewhat more consistent with an atmosphere. But the constraints ruled out a thick Venus-like CO2-dominated atmosphere. TRAPPIST-1c likely has a thin or absent atmosphere. The result was initially presented as somewhat discouraging for the broader system, but a closer analysis of what it means for the outer planets is more nuanced. TRAPPIST-1b and TRAPPIST-1c are well inside the habitable zone, hotter, subject to more intense EUV flux, with less initial volatile inventory. They're closer to the star and probably accreted there, or migrated through a region where volatile retention during migration was more difficult. They represent the inner boundary case. The results for B and C tightening the constraints on the inner system do not straightforwardly translate to the same conclusions for TRAPPIST-1e, F, and G. The transmission spectroscopy observations of TRAPPIST-1e are underway and ongoing. The signal JWST is looking for, the atmospheric transit depth variations caused by CO2 or water vapor absorption, requires accumulating signal over many transits, because each individual transit contributes only a small amount of signal to noise at the required or precision level. The current approved observing programs for TRAPPIST-1e allocate dozens of transit observations using JWST's NIR spec and NIRISS instruments, with the expectation that statistically meaningful constraints on the atmospheric composition will emerge from the combined dataset within the next 1 to 2 years. The specific detection JWST is most likely to make first, if an atmosphere is present, is the CO2 absorption feature at 4.3 micrometers. Carbon dioxide has a strong, distinctive absorption signature at this wavelength, and JWST's NIRCam and NIR spec instruments have good sensitivity there. On Earth, a CO2 detection would be a hint of volcanism or biology, but on TRAPPIST-1e, a CO2 detection would be primarily evidence that an atmosphere exists at all, and that it has been outgassed from a geologically active interior. That alone would be transformative for our understanding of the TRAPPIST-1 system, and for the broader question of whether M-dwarf habitable zone planets can retain atmospheres. The next detection priority after CO2 would be water vapor, which would directly constrain the surface water inventory and atmospheric humidity. Key inputs for climate models of the planet's surface temperature distribution. And the detection that would electrify the scientific community is one that no JWST program has yet achieved on any planet. A simultaneous detection of oxygen and methane, both in the same atmosphere, at concentrations that are chemically inconsistent with abiotic production. On Earth, atmospheric oxygen and methane are maintained at biologically regulated concentrations. Without ongoing biological production, the two molecules would rapidly react with each other and destroy each other's signal. Their simultaneous presence at detectable concentrations is the strongest atmospheric biosignature in current astrobiology theory. That detection is likely years away for TRAPPIST-1e, if it's achievable at all, with JWST. The individual molecular signals are at or below JWST's detection threshold for a single Earth-like atmosphere. But the direction of travel is clear. The next few years of JWST observations will determine whether TRAPPIST-1e has an atmosphere, what it's made of, and whether the surface conditions are consistent with liquid water. It's worth dwelling on this last point, whatever they are, because a null result from the JWST TRAPPIST-1e program would itself be a significant scientific finding, not a failure. If JWST accumulates enough transit observations of TRAPPIST-1e to rule out the presence of a CO2-rich atmosphere with a sensitivity comparable to Earth's atmospheric CO2 concentration, and finds no atmospheric signal, that would be evidence that TRAPPIST-1e's atmosphere has been stripped to trace levels, a real and informative outcome. It would tell us that M-dwarf habitable zone planets, even at TRAPPIST-1e's orbital distance, cannot retain atmospheres through the early active stellar phase, which would have major implications for the estimated frequency of habitable worlds in the galaxy. Most rocky planets in habitable zones are around M-dwarfs because M-dwarfs are the most common type of star. If their habitable zone planets are routinely stripped of atmospheres, the galaxy's habitable real estate is considerably smaller than optimistic estimates suggest. A positive detection, CO2, confirmed, atmosphere present, would be the opposite. Confirmation that the atmospheric retention mechanisms we've discussed, high initial volatile inventory, outgassing, possible magnetic shielding, are sufficient to preserve atmospheres on at least some M-dwarf habitable zone planets. Every transit observation of TRAPPIST-1e being processed through JWST's data pipeline right now is either accumulating toward that detection or toward that constraint. Either answer is transformative. This is what real science at the frontier looks like. That is the most significant atmospheric characterization program ever attempted for a potentially habitable world, and the results, whatever they are, will redefine the field. Chapter 8: The Red Light Problem. Photosynthesis. Under a crimson sun. If TRAPPIST-1e has an atmosphere and liquid surface water, the next question for habitability is whether life could actually do anything useful with the light it receives, because the light from TRAPPIST-1 is profoundly different from sunlight, in ways that matter deeply for the most important chemical reaction in Earth's biosphere: photosynthesis, the process by which organisms convert light energy into chemical energy, driving essentially all of the food webs on Earth's surface, is tuned to the solar spectrum. The chlorophyll molecules that plants and cyanobacteria use to absorb light have absorption peaks at approximately 430 and 680 nanometers in the blue and red parts of the visible spectrum. The sun emits most of its energy between 400 and 700 nanometers, visible light, with a peak around 500 nanometers, right in the middle of the wavelength range that chlorophyll can use. This is not a coincidence. Life on Earth evolved its photosynthetic machinery under solar illumination, and the chemistry of chlorophyll is adapted to capture what the sun provides most abundantly. TRAPPIST-1 emits most of its energy at longer wavelengths. Its peak emission is around 1,100 nanometers. In the near infrared, well beyond the visible range. It emits roughly 70 to 80% of its total light output at wavelengths longer than 700 nanometers, where conventional plant chlorophyll absorbs very weakly. The fraction of TRAPPIST-1's output in the 400 to 700 nanometer range that Earth plants use most efficiently is only about 10 to 15% of the star's total luminosity. In absolute terms, a planet receiving 66% of Earth's total stellar flux from TRAPPIST-1 is getting substantially less photosynthetically useful visible light than Earth does from the sun. This sounds like a fundamental problem. But the biology of photosynthesis is more flexible than the chlorophyll-centric Earth picture suggests. And the physics of near-infrared photosynthesis opens up possibilities that make the situation significantly more interesting. First, the flexibility point. Chlorophyll is not the only photosynthetic pigment that has evolved on Earth. Purple bacteria use bacteriochlorophyll, which has absorption peaks at 800 and 850 nanometers in the near-infrared. Some anoxygenic photosynthetic bacteria use pigments absorbing at wavelengths up to 1,050 nanometers. These organisms are primarily aquatic, operating in conditions where visible light has been filtered out by water or competing organisms above them. They evolved to harvest whatever photons were available in their specific niche, demonstrating that biology is capable of engineering photosynthetic machinery to operate at longer wavelengths when evolutionary pressure selects for it. On TRAPPIST-1e, if life evolved from scratch under red dwarf illumination, there would be powerful evolutionary selection pressure to develop photosynthetic pigments absorbing in the near-infrared, the wavelength range where photons are most abundant. The resulting photosynthesis would look nothing like chlorophyll-based plant photosynthesis. It might use pigments absorbing primarily at 800 to 1,100 nanometers. It might appear very dark, even black to our eyes, absorbing across the visible and near-infrared to capture as much of the available light as possible. Biologists studying this possibility have proposed the existence of black leaves, or analogous dark photosynthetic structures, on red dwarf planets, organisms that would look visually very different from Earth's green biosphere, but would be doing the same fundamental job of converting starlight to chemical energy. Now the physics point. The question of how productive near-infrared photosynthesis could be is partly a question of photon flux, not just photon energy. Photosynthesis requires a minimum energy per photon to drive the photochemical reaction. The energy required to split water and produce oxygen in oxygenic photosynthesis is the binding energy of the OH bond in water, roughly equivalent to a photon at about 1,100 nanometers. So near-infrared photons at 800 to 1,000 nanometers have enough energy, individually, to drive photosynthetic reactions. They just have less energy per photon than blue visible photons. This energy per photon difference means that near-infrared photosynthesis requires more photons per unit of stored chemical energy than visible light photosynthesis does. But the key question is whether there are enough photons available. And this is where TRAPPIST-1E's situation becomes interesting, because TRAPPIST-1 emits so much of its energy in the near-infrared, the total photon flux at near-infrared wavelengths on TRAPPIST-1E's surface may actually be higher than the visible photon flux on Earth's surface. More photons available, each carrying somewhat less energy, but enough energy to drive the reaction. A 2018 study by Sarah Ruegheimer and colleagues at Cornell used detailed atmospheric models to calculate the photon flux at the surface of TRAPPIST-1E across the full relevant wavelength range. The result? The photosynthetically active radiation at TRAPPIST-1E's surface, integrated over the wavelength range usable by a hypothetical infrared adapted photosynthetic system, is comparable to, and in some wavelength bands exceeds, the equivalent flux on Earth's surface. An organism evolved to harvest near-infrared photons on TRAPPIST-1E would not be starved of light. It would be photosynthesizing in a rich photon environment, just at longer wavelengths than Earth biology uses. The surface would look strange. The dominant color of TRAPPIST-1E's vegetation, if it has any, would not be green. The red edge, the sharp increase in reflectance at 700 nanometers that makes Earth's vegetation detectable from space as a spectroscopic signature, would be replaced by whatever cutoff wavelength the infrared photosynthetic pigments stop absorbing at. TRAPPIST-1E's vegetation red edge, if it exists, might be at 900 or 1000 nanometers, visible only in infrared imaging. The landscape, illuminated by a faint brownish red star lit by perpetual, oblique light near the terminator, covered in dark or black photosynthetic organisms, under a sky that probably glows in deep red and near infrared, would be unlike anything in human visual experience, but it would not be dark or lifeless or biologically starved. The detectability of a TRAPPIST-1E biosphere from Earth is not purely academic. It connects directly to what JWST and future telescopes are actually searching for. On Earth, the presence of a photosynthetic biosphere produces a distinctive spectroscopic signature called the vegetation red edge. A sharp increase in the reflectance of Earth's surface at approximately 700 nanometers, where chlorophyll stops absorbing and plant tissue becomes highly reflective. This step change in albedo is detectable in Earth's disk-integrated spectrum and would in principle be visible in remote spectroscopy of an Earth-like planet from a distant telescope. On TRAPPIST-1E, any equivalent vegetation signature would be shifted to longer wavelengths. If the dominant photosynthetic pigments absorb up to 900 or 1000 nanometers before becoming transparent, the red edge equivalent would be an infrared edge at those wavelengths. JWST and the ELT can observe in the near-infrared with high sensitivity, which means a TRAPPIST-1E vegetation signature. If it exists, and if the biosphere is productive enough to contribute a measurable signal to the planet's disk-integrated spectrum, might actually be observable. It's a long chain of conditional probabilities. The biosphere has to exist, has to cover enough of the surface to produce a detectable signal, and the signal has to be large enough to distinguish from non-biological surface spectral features. But the conceptual pathway from photosynthetic life on TRAPPIST-1e to a detectable remote biosignature is not blocked by any physical barrier. It runs through the near-infrared, where our best telescopes are already looking. There is one more dimension to the photosynthesis, questions specific to tidally locked planets. The light environment is spatially stable in a way Earth's never is. A photosynthetic organism on TRAPPIST-1e's terminator belt does not experience the diurnal cycle of day and night that drives the alternating light and dark phases of photosynthesis and cellular respiration on Earth. The light level is constant, perpetual oblique illumination. This has interesting evolutionary implications. The complex regulatory machinery that Earth plants use to switch between photosynthesis and respiration, to track the daily light cycle, to prepare for sunset and sunrise, would be unnecessary. Simpler, more streamlined photosynthetic systems might be sufficient. On the other hand, the lack of a day-night cycle removes a major organizational rhythm that structures activity patterns in Earth organisms. How biology would adapt to perpetual light at the terminator is genuinely unknown, but it is not obviously a disadvantage. Chapter 9: Life's Chemistry. Does TRAPPIST-1e have the right ingredients? Photosynthesis is one chemical reaction. Life is millions of them. For any of them to happen on TRAPPIST-1e, the planet needs the right elemental ingredients and the right physical and chemical environment in which those ingredients can react. The elemental requirements for life as we know it, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, plus a toolkit of trace metals, are among the most cosmically abundant elements. Carbon, oxygen, and hydrogen are the three most abundant reactive elements in the universe. Nitrogen and sulfur are common products of stellar nucleosynthesis. Phosphorus is less abundant, but present in rocky planets formed from solar composition material. There is no known reason why TRAPPIST-1e would be elementally deficient relative to Earth. It formed from the same stellar nebula material in a star system with approximately solar elemental abundances. The building blocks of biochemistry are there. What about liquid water? We've established that TRAPPIST-1e likely has a large water inventory, possibly much larger than Earth's. The question is whether that water is in liquid form on the surface, or if it exists in states that are biologically less accessible. Deep ice under the pressure of a global ocean, high-temperature steam in a thick greenhouse atmosphere, or ice on a fully glaciated surface. The answer depends on the atmospheric pressure and composition, which depend on the atmospheric inventory, which depends on whether the planet retained its atmosphere through the early stellar activity phase. The chain of dependencies we've already discussed. But if we assume, and this is a scientific assumption, not a certainty, that TRAPPIST-1e has retained a substantial atmosphere with a moderate greenhouse effect, then the surface conditions for liquid water are met. The climate model runs for TRAPPIST-1e with Earth-like atmospheric compositions consistently produce surface liquid water in at least some regions of the planet, and usually across most of the surface, in the models, with atmospheric pressures above about 1 bar. Liquid water on the surface means the potential for the full range of aqueous chemistry that life requires. The carbonate-silicate cycle, the feedback that regulates Earth's long-term climate by drawing down CO2 from the atmosphere into carbonate rocks when the climate warms, operates in liquid water. The dissolution and transport of minerals, the pH buffering that makes most cellular chemistry possible, the hydrothermal systems where many astrobiologists believe life may have originated on Earth. All of these require liquid water, and specifically liquid water in contact with rocky surfaces. A shallow ocean covering TRAPPIST-1E's surface, with an active geology below providing chemical gradients and minerals, would have all of these available. The tidal heating we discussed in the previous chapter adds a specific chemical richness to the picture. On Io, Jupiter's innermost moon, the tidal heating is so extreme that the surface is resurfaced by volcanism every few thousand years, continuously bringing fresh material from the interior to the surface. On TRAPPIST-1E, the tidal heating is expected to be at a much more moderate level, but still potentially significant enough to maintain an active system of ocean floor venting and volcanism. Hydrothermal vent systems on the ocean floor, systems like those found in Earth's mid-ocean ridges and spreading centers, are among the most chemically rich environments on Earth, continuously releasing reduced chemical compounds from the hot, mineral-laden fluids that have circulated through the rocky seafloor. These are exactly the kinds of chemical gradients that many origin of life theories regard as essential for the initial emergence of self-replicating chemistry. A TRAPPIST-1E with a global shallow ocean and a tidally heated geological interior would not merely have water. It would have water continuously enriched by fresh mineral input from the interior. A chemically active hydrosphere maintained in a dynamic state by the gravitational energy of the planetary system. The resonance-driven tidal heating is, in this sense, not just a source of interior warmth, but a continuous chemical engine, driving the kinds of far-from-equilibrium chemistry that life exploits. The specific setting of the origin of life on Earth is still debated, but two environments dominate current thinking: submarine hydrothermal vents and warm, shallow tidal pools. In the hydrothermal vent scenario, associated particularly with the work of Mike Russell and Nick Lane, life arose at alkaline hydrothermal vents on the early ocean floor, where proton gradients across mineral membranes provided the original energy source for the first metabolisms, and where the continuous flux of reduced compounds from the hot vent fluids created the chemical disequilibrium that drives biochemistry. In the shallow pool scenario, associated with Darwin's original warm little pond idea, and developed more recently by researchers including John Sutherland, life arose in surface pools that experienced wet-dry cycles, concentrating organics and driving the condensation reactions that formed the first polymers. TRAPPIST-1E's ocean chemistry is potentially well-suited to both environments. A global ocean with active seafloor geology, driven by tidal heating, would support extensive hydrothermal vent systems. In fact, potentially more extensive than Earth's, given the larger total ocean area and the tidal heating supplement that maintains geological activity. Whether TRAPPIST-1E has exposed land with shallow tidal pools is less certain. A deep global ocean might have no exposed surface at all, but ocean ridge systems and volcanic seamounts could break the surface in a water-rich but not completely drowned world, creating the shallow volcanic island environments that some origin of life researchers favor. The wet-dry cycling scenario deserves a specific note for TRAPPIST-1e. On a tidally locked world without conventional tides driven by a large moon, the tidal forcing of the ocean surface is different from Earth's. There is no lunar day-night tidal cycle. Instead, the permanent tidal bulge from the star itself creates a permanent equatorial asymmetry in ocean depth, and the tidal heating from orbital eccentricity drives periodic flexing. Whether this produces anything like the coastal wet-dry cycling relevant to origin of life chemistry in shallow pools is not clear. But the ocean itself, rich in dissolved minerals from active seafloor volcanism, potentially with exposed volcanic islands, in a thermally diverse environment spanning the warm day side to the cooler night side, provides a range of chemical environments more diverse than any single origin of life scenario requires. There is one chemical challenge specific to red dwarf planets that deserves attention: the photochemistry of the atmosphere. On Earth, the sun's ultraviolet radiation drives important atmospheric chemistry, including the formation of the ozone layer that shields the surface from damaging shorter wavelength UV. TRAPPIST-1 emits very little UV at the wavelengths most important for ozone formation. A TRAPPIST-1e atmosphere might have a very different photochemical balance from Earth's. Less ozone formation, but also a different distribution of reactive oxygen species and radical chemistry throughout the atmosphere. The consequence is not straightforward. Less ozone means less UV shielding of the surface, a potential hazard for surface life, as we discussed in the context of flares in Part 1. But it also means less UV-driven destruction of certain atmospheric molecules. Methane and complex organic molecules can persist in a low UV atmosphere for much longer timescales than they do on Earth, where UV photolysis continuously breaks them down. A low UV atmosphere on TRAPPIST-1e might build up interesting complex chemistry over geological timescales, potentially including the kinds of organic molecules relevant to prebiotic chemistry. Whether this is a habitability advantage or disadvantage depends on the specific chemistry and the specific life. But it's another dimension in which TRAPPIST-1e's chemistry would be genuinely different from Earth's, not simply worse. Chapter 10: The Resonance Engine. 7 planets. Talking to each other. TRAPPIST-1e does not exist in isolation. It is the 4th planet in a system of 7, and the gravitational conversations between all 7 of them are one of the most distinctive features of this system. Distinctive in ways that are directly relevant to habitability. The 7 TRAPPIST-1 planets are in a near-resonant orbital chain. Their orbital period ratios are close to simple integer fractions. B to C near 8 to 5, C to D near 5 to 3, D to E near 3 to 2, E to F near 3 to 2, F to G near 4 to 3, G to H near 3 to 2. This near resonance is the signature of a migration history. The planets formed further from the star in regions of the protoplanetary disk rich in volatiles beyond the ice line, and then migrated inward through interactions with the disk gas, settling into the resonant chain as they encountered each other during migration and were captured into resonant relationships. This migration history is the reason the planets are so volatile rich. They brought their ice-dominated compositions with them when they moved inward. The resonant architecture has a direct, measurable consequence. It maintains small but non-zero eccentricities in the orbits of all the planets. Perfect circular orbits are rare in resonant systems. The resonant interactions continuously pump energy back and forth between the planets, driving slight orbital ellipticities. TRAPPIST-1. E's orbital eccentricity is estimated at approximately 0.006 to 0.01 based on the current best-fit orbital solutions from transit timing variation modeling. This is very small. Earth's eccentricity is 0.017 for comparison, but it is not zero. And even a small, non-zero eccentricity for a planet this close to its star has a meaningful effect. The effect is tidal heating. When TRAPPIST-1e is at its closest point to the star, periapsis, in its slightly elliptical orbit, the tidal force stretching the planet is slightly larger than when it is at its furthest point, apoapsis. This periodic variation in the tidal force as the planet goes around its orbit causes the planet to flex slightly, to be stretched and squeezed rhythmically at the orbital period of 6.1 days. Internal friction in the planet converts this mechanical energy of deformation into heat. The heat is generated throughout the planet's interior, but is concentrated in regions where the mantle is most viscous and where the conversion of strain energy to thermal energy is most efficient. The estimated tidal heating rate for TRAPPIST-1e under the current best-fit orbital parameters is uncertain, but spans a range from roughly comparable to Earth's radiogenic heat production to several times higher, depending on the assumed mantle, viscosity, and tidal dissipation efficiency. Earth's internal heat budget is approximately 47 terawatts, about 0.09 watts per square meter of surface area. Models of TRAPPIST-1e's tidal heating suggest a potential range from a fraction of this value up to perhaps twice it. Even at the lower end of this range, the tidal supplement to radiogenic heating makes a meaningful difference to the geological activity of a planet that, at only 0.69 Earth masses, would otherwise be expected to have cooled significantly more than Earth over a comparable timescale. What does this geological activity mean for the surface? On Earth, the primary expressions of internal heat reaching the surface are plate tectonics, volcanism, and hydrothermal circulation. Plate tectonics, the movement of large, rigid crustal plates over a more fluid underlying mantle, is the mechanism by which Earth recycles its crust, drives the carbonate-silicate cycle that regulates atmospheric CO2, and creates the varied topography, mountains, ocean ridges, subduction trenches, that provides diverse ecological habitats. Whether TRAPPIST-1e has plate tectonics is not known and may not be knowable with current observations, but the tidal heating that supplements its internal heat budget makes plate tectonics more likely to be active than it would be for an isolated planet of the same mass. Less massive, less heated planets tend to lose their plate tectonics as they cool. Mars is the relevant example in our solar system, where plate tectonics ceased roughly 4 billion years ago and was replaced by the stagnant lid regime we observe today. TRAPPIST-1e's tidal supplement could be the difference between a Mars-like geologically dead planet and an Earth-like geologically active one. The stagnant lid scenario deserves elaboration because it illustrates precisely why the tidal heating matters so much for TRAPPIST-1e's long-term habitability. planet in stagnant lid mode has a single, thick, rigid crust that doesn't recycle into the mantle. Without crustal recycling, the carbonate-silicate cycle stalls. Carbon dioxide builds up in the atmosphere from volcanic outgassing, but the mechanism that draws it back down, the subduction of carbonate-bearing seafloor and its subsequent re-emission from arc volcanoes, doesn't operate. On Mars, the result was that any early thick atmosphere either escaped to space or was drawn into the crust as carbonates, leaving the thin, mostly CO2 atmosphere we observe today. Venus may represent the opposite end of the stagnant lid outcome. Thick CO2 atmosphere, no crustal recycling, catastrophic runaway greenhouse. Earth's plate tectonics prevents both failures. The carbon cycle, driven by plate tectonics, acts as a climate thermostat on multi-million-year timescales. When Earth warms, silicate weathering speeds up, drawing down CO2 and cooling the planet. When it cools, weathering slows, CO2 builds up, and the greenhouse warms things back. This negative feedback has kept Earth's climate within the range of liquid water for over 4 billion years, despite the sun's luminosity increasing by about 30% in that time. If TRAPPIST-1e were in stagnant lid mode, which is 0.69 Earth mass planet in an isolated orbit might well be, having cooled more than Earth over 5 to 8 billion years, it would face exactly these long-term climate regulation failures. The tidal heating from the resonant orbital chain is the specific mechanism that may prevent this. Keeping the interior hot enough maintains the mantle convection that drives plate tectonics. Maintaining plate tectonics maintains the carbonate-silicate cycle. Maintaining the carbonate-silicate cycle maintains the long-term climate thermostat that keeps liquid water on the surface across geological timescales. The 7-planet resonant chain is not just an interesting dynamical curiosity. It may be the mechanism that keeps TRAPPIST-1e's carbon cycle running and its climate stable over timescales that a planet of its mass in isolation could not sustain. The system architecture matters in another way. The mutual gravitational interactions between all 7 planets act as a long-term stabilizer of the resonant chain. Resonant systems can be stable for billions of years because the resonances that drive eccentricity pumping also provide restoring forces when perturbations try to disrupt the configuration. Numerical n-body simulations of the TRAPPIST-1 system consistently find stability timescales of at least 1 billion years, and many find stability for the full current estimated age of the system. The 7 planets are not in a precarious dynamical configuration on the verge of instability. They are in a self-reinforcing, resonant chain that is likely to persist for the full remaining main sequence lifetime of the star. This dynamical stability is significant for life on TRAPPIST-1e. A catastrophic orbital instability, 2 planets exchanging orbits, ejecting one from the system or colliding, would reset the habitability clock on any surviving planet and would certainly be lethal to any biosphere present. The fact that the TRAPPIST-1 resonant chain has persisted for billions of years and is predicted to continue doing so means that TRAPPIST-1e's surface conditions have been relatively stable over the timescales relevant to biological evolution. Climate fluctuations from orbital changes, the Milankovitch cycles that drive Earth's ice ages, are different in a resonant, tidally locked system, but the catastrophic orbital instability that might otherwise reset the biosphere is not in the cards. Chapter 11. Scoring TRAPPIST-1e. How does it actually compare? Let's step back from individual parameters and look at the full picture. We've examined TRAPPIST-1e against the major axes of the super habitability framework. It's time to actually score it. Start with what genuinely favors TRAPPIST-1e over Earth. Stellar longevity is the most unambiguous advantage. TRAPPIST-1 has a remaining main sequence lifetime of approximately 10 trillion years. The Sun has about 5 billion years remaining. The ratio is 2,000 to 1. Any biosphere on TRAPPIST-1e that gets started has available to it a window of stellar stability 2,000 times longer than Earth currently has. In terms of evolutionary opportunity, nothing else in the comparison comes close to this number. Water inventory, while uncertain in its surface expression, strongly favors TRAPPIST-1e. Even conservative estimates of its water mass fraction are 50 to 250 times higher than Earth's. If that water is distributed as shallow productive seas rather than crushing deep abyssal ocean, the total area of biologically productive shallow marine habitat could be orders of magnitude larger than on Earth. The biosphere that this supports, if the conditions for life are met, would be more productive, more diverse, and more resilient than Earth's, simply by virtue of the vastly larger habitat area. Stellar age advantage potentially favors TRAPPIST-1e, though with significant uncertainty. TRAPPIST-1 is almost certainly older than the Sun, probably 5 to 8 billion years old, versus the Sun's 4.6 billion. If the habitable phase of TRAPPIST-1e began early and has been maintained continuously, the biosphere there has had more time to evolve. For every extra billion years of evolutionary time, the probability of the emergence of greater biological complexity increases. Whether TRAPPIST-1e's biosphere has been running continuously since the habitable phase began, or whether it was disrupted by the early active stellar phase and had to restart, is the key unknown. But the time advantage is real if the biosphere has been stable. Tidal heating for TRAPPIST-1e, specifically within the TRAPPIST-1 system, may be providing the geological activity that a planet of 0.69 Earth masses might otherwise have largely lost by now. For a planet that size in an isolated orbit, we'd expect significant cooling of the interior over 5 to 8 billion years, with reduced volcanism and potentially stagnated plate tectonics. The tidal supplement from the resonant orbital chain is keeping TRAPPIST-1e warmer inside than its mass and age alone would predict. This is a specific advantage over an isolated Mars-sized world, though not necessarily over Earth. The near-infrared ice albedo effect is a subtle but real advantage for climate stability, because ice on TRAPPIST-1e reflects much less of the incoming stellar radiation than ice on Earth reflects sunlight. The ice albedo positive feedback that drives Earth into full glaciations is greatly damped on TRAPPIST-1e. A TRAPPIST-1e that begins to cool and develop surface ice does not experience the runaway ice albedo feedback that might drive it to a snowball state. This makes the climate more stable against glaciation. Biologically valuable because snowball Earth episodes have been among the most severe disruptions to Earth's biosphere in the geological record. Now, for what genuinely works against TRAPPIST-1e, planetary mass is a real shortcoming at 0.69 Earth masses. Lower surface gravity means less efficient long-term atmosphere retention. A smaller planet generates less radiogenic heat, partly compensated by tidal heating, as noted. The lower mass also means a thinner core and potentially weaker magnetic dynamo, potentially weaker magnetic field protection against stellar wind erosion of the atmosphere. These are genuine marks against habitability, and they are not fully compensated by the tidal heating supplement. Early stellar activity is the most fundamental challenge, not because the current TRAPPIST-1 is particularly hostile, but because the young TRAPPIST-1 may have been. The first 1 to 2 billion years of the system's history, when TRAPPIST-1 was more magnetically active and the EUV/XUV flux was higher, was the period most dangerous for atmosphere retention. The inner planets, TRAPPIST-1b and c, appear to have lost their atmospheres. Whether TRAPPIST-1e, further from the star and subject to less intense escape forcing, retained a meaningful volatile inventory through this phase is the pivotal unknown. The JWST data will address this. Tidal locking, while less disqualifying than it was once thought, is still a climate complication that Earth doesn't have. Earth's 24-hour rotation drives a global atmospheric circulation pattern that efficiently redistributes heat across all latitudes and longitudes. TRAPPIST-1e's permanently locked rotation creates a more extreme spatial differentiation. Even with atmospheric circulation, the day-night temperature difference is greater than anything on the rotating Earth. This creates more extreme spatial gradients in weather, precipitation, and surface conditions, which could be either a complication for life or a source of diverse ecological niches depending on how you look at it. Flare radiation remains an ongoing hazard. TRAPPIST-1 is a flaring star today, not just in youth. While the current flares are less extreme than the early phase, they are still more frequent and energetic per unit surface area at TRAPPIST-1e's orbital distance than solar flares experienced at Earth. Surface life without adequate atmospheric shielding or biochemical UV protection would face a challenging radiation environment during flare events. There is one more framing of the superhabitability comparison that is worth being explicit about, because it changes how you should interpret everything in this chapter. The superhabitability framework is not claiming that TRAPPIST-1e is probably inhabited. It is claiming that, conditional on life having arisen there, TRAPPIST-1e's environment is in several respects more conducive to biodiversity and biological persistence than Earth's. The distinction matters. You can think of it this way. If you took all the rocky habitable zone planets in the galaxy and ranked them on a superhabitability index, a composite score across stellar longevity, water inventory, planetary mass, surface temperature, and age, the resulting distribution would have most planets near some median value, with tails toward very high and very low scores. Earth's score is not 100 out of 100. Earth is one data point in the middle of a distribution. Some planets in the galaxy score lower, drier, colder, shorter-lived stellar hosts. And some score higher, wetter, warmer, older stars that will burn for longer. TRAPPIST-1e, by the specific metrics we've examined, appears to be in the upper tail of this distribution on several axes simultaneously. This does not mean life is more likely to have started on TRAPPIST-1e than on Earth. The origin of life is a separate question, perhaps the hardest question in all of science, and we have no working quantitative model for the probability of abiogenesis per unit time, per unit of planetary surface area. TRAPPIST-1e might score higher on the superhabitability index and still be lifeless if life never got started there. But if life did get started, if the same chemical spark that happened on the early Earth happened on early TRAPPIST-1e, then the environment TRAPPIST-1e provides for the subsequent evolution and elaboration of that life is, by multiple measurable criteria, more generous than the one Earth provides. Put all of this together, and the scorecard is genuinely mixed, but mixed in a way that's interesting, not dismissive. TRAPPIST-1e does not sweep the superhabitability criteria, but it scores distinctively higher than Earth on several of them: long-term stellar stability, water inventory, possibly age, while being disadvantaged on others. It is not obviously inferior to Earth as a habitat for life. In the specific framing of the Heller-Armstrong superhabitability paper, TRAPPIST-1e scores comparably to Earth on the overall index, with individual strengths and weaknesses that make direct comparison difficult. What the comparison does establish is that the question is not absurd. Is TRAPPIST-1e more habitable than Earth? Is not a clickbait provocation. It is a scientific question with a genuinely uncertain answer that depends on measurable properties of the planet that we are, right now, in the process of measuring. Chapter 12. The Road Ahead. What we'll know in 10 years? The frustrating and exciting reality of TRAPPIST-1e science is that the most important questions are in the process of being answered, not already answered. The next decade will transform what is currently a detailed theoretical case into a data-driven one, or will narrow the space of viable scenarios dramatically. Here is what the observational program over the next 5 to 15 years is expected to deliver. The most immediate deliverable is the JWST transmission spectroscopy program for TRAPPIST-1e currently underway. By 2026 to 2027, depending on how many approved transit observations have accumulated, we should have statistically meaningful constraints on whether TRAPPIST-1e has a CO2-bearing atmosphere at Earth-equivalent concentrations. This is not a guaranteed detection. It is a constraint. If the atmosphere is present and CO2-rich, and if the atmospheric pressure is above about 0.1 bar, the signal should be detectable at the few sigma level with JWST's accumulating dataset. If the atmosphere is thin or absent, the JWST data will place upper limits on the atmospheric column density that rule out the most optimistic scenarios. The timescale for this result is not indefinite. TRAPPIST-1e has a transit every 6.1 days. Approved JWST programs have scheduled dozens of transit observations over the instrument's lifetime. By 2026 or 2027, the accumulated signal-to-noise will begin to reach scientifically meaningful levels for CO2 detection. If positive, the result will be announced rapidly. Atmospheric detections on habitable zone planets are the kind of result that does not stay in pre-publication for long. If constraining rather than detecting, the scientific community will have a more precisely bounded parameter space to work with for subsequent theoretical modeling. The second JWST deliverable for TRAPPIST-1e is more ambitious: water vapor detection in transmission. Water vapor has stronger and more numerous absorption features than CO2 across JWST's wavelength coverage, but it is also more variable and more subject to confusion with stellar contamination effects. The phenomenon, where the star's own surface heterogeneity introduces spurious spectral signals into the transmission spectrum. Extracting a clean water vapor detection from TRAPPIST. 1E's transmission spectrum requires modeling and subtracting these stellar contamination signals, which is a technically demanding analysis. The timescale for a robust water vapor detection, if it exists, is probably 2027 to 2029 with the JWST dataset. Beyond JWST, the next major development in the characterization of TRAPPIST, 1E, will come from the next generation of extremely large ground-based telescopes. The Extremely Large Telescope, ELT, being constructed in Chile by the European Southern Observatory, expected to begin science operations around 2028. The Giant Magellan Telescope, GMT, also in Chile, expected around 2029. And the 30-meter telescope, TMT, whose construction has faced site selection delays but is expected in the early 2030s. These instruments have primary mirrors of 25 to 39 meters, far larger than any existing telescope, and will be capable of atmospheric spectroscopy of TRAPPIST-1E with sensitivity that complements JWST in important ways. In particular, the ELT's high-resolution spectrograph, called ANDES, formerly known as HIRES, will be capable of resolving individual spectral lines in TRAPPIST-1E's atmospheric spectrum, rather than just detecting broad molecular bands. High-resolution spectroscopy can distinguish the Doppler-shifted signal of the planet's atmospheric lines from the stellar spectrum and from telluric absorption in Earth's own atmosphere with much greater precision than space-based observations at lower resolution. This means the ELT may be able to detect not just CO2 and water vapor, but weaker molecular signals, including oxygen and ozone, molecules whose simultaneous presence would constitute the strongest available biosignature for photosynthetic life. The ELT's Andes spectrograph operating on TRAPPIST-1E is the realistic pathway to a biosignature detection, not guaranteed, but within the instrument's theoretical capability. The timing works out to something like this. JWST results on CO2 and water vapor by 2027 to 2029. ELT and GMT first science. In 2028 to 2030, with initial TRAPPIST-1E observations following as the instruments are commissioned. Combined JWST and ground-based data giving meaningful oxygen or ozone constraints in the early 2030s. If TRAPPIST-1E has a rich enough atmosphere and a photosynthetic biosphere active enough to maintain significant atmospheric oxygen, we might know by 2033 to 2035. Before arriving at that timeline, it's worth stepping back and appreciating why the TRAPPIST-1E observational program matters beyond the question of whether this specific planet has life. The TRAPPIST-1 system is the best studied compact M-dwarf planetary system we have found, and what we learn from it generalizes. M-dwarf stars constitute approximately 75% of all stars in the Milky Way. If their habitable zone rocky planets are routinely habitable, if TRAPPIST-1E turns out to have an atmosphere and potentially a biosphere, then the number of potentially habitable worlds in the galaxy increases by an enormous factor. there are an estimated 40 billion rocky planets in the habitable zones of M-dwarf stars in the Milky Way alone. If even 1% of them are habitable, that's 400 million habitable worlds in our galaxy. If, on the other hand, TRAPPIST-1e turns out to be airless, stripped by early stellar activity, geologically stagnant, chemically barren, then M-dwarf habitable zone planets as a class are probably not habitable, and the 40 billion candidates reduced to near zero. The galaxy's habitable real estate would then be confined primarily to the rarer G-dwarf and K-dwarf systems. The frequency of habitable worlds in the galaxy changes by orders of magnitude depending on which way the TRAPPIST-1e data go. This is a genuinely consequential observation program, not just for TRAPPIST-1e itself, but for the entire question of how common life might be in the universe. That is an extraordinary statement to be able to make. We might know within roughly a decade whether there is photosynthetic life on a planet 40 light years away. Not we might have a hint, or we might have a marginal signal at 2 sigma. We might have a confirmed atmospheric biosignature on TRAPPIST-1e by the time the children starting primary school today finish their undergraduate degrees. There is one more observational program that will contribute critical context for interpreting the atmospheric results. The continued refinement of the system's orbital dynamics through transit timing variation analysis. As more transit observations accumulate, both from JWST and from dedicated ground-based monitoring campaigns, the mass estimates for all 7 planets will improve, narrowing the uncertainty on TRAPPIST-1e's density and therefore on its water mass, fraction, and interior structure. Better interior models will constrain the tidal heating rate more precisely, improving predictions for the geological activity that drives outgassing, and potentially the magnetic field. The picture that emerges from all of this, if it emerges as the optimistic scenario, is a rocky world with a CO2H2O atmosphere, warm seas, active geology, a geological interior heated partly by the resonant orbital interactions of its 6 sibling planets, and potentially a photosynthetic biosphere adapted to near-infrared light from a small, ancient, dim red star that will burn for another 10 trillion years. A world older than Earth, wetter than Earth, with more evolutionary time available than Earth, sitting 40 light years away. If it doesn't emerge, if JWST finds that TRAPPIST-1e is as airless as TRAPPIST-1b appears to be, then we will have learned something deeply important about the habitability of M-dwarf planets in general, and the search for life in the universe will shift toward K-dwarf and G-dwarf planets as the primary targets. Either outcome reshapes astrobiology. That is the nature of genuinely important observations. Conclusion: why TRAPPIST-1e is the most important planet we've ever found. There is a version of the conclusion to this video that ends with appropriate scientific caution. TRAPPIST-1e might not have an atmosphere. It might be a bare, radiation-scorched rock. The early stellar activity might have stripped it bare. The superhabitability case might be theoretical, and the actual planet might be another Io, geologically active and biologically barren. All of that is possible, and all of it would be a useful scientific finding. But let's also be honest about what the case actually amounts to when you put it together completely. TRAPPIST-1e orbits a star that will outlive everything else we can see by a factor of 1,000. It sits in the middle of that star's habitable zone, receiving 2/3 of Earth's stellar flux, with a spectral quality of light that is more resistant to driving runaway glaciation than Earth's sunlight. Its density measurements are consistent with a water inventory 50 to 250 times richer than Earth's. Its orbital architecture, 7 planets in a resonant chain, all of them migrated inward from volatile, rich outer regions of the protoplanetary disk, gives it a geological interior likely still active from tidal heating despite its 5 to 8 billion year age. Its climate, if it has an atmosphere, would be regulated by powerful atmospheric circulation patterns that prevent the thermal extremes you might naively expect from a tidally locked world. Its photosynthetic niche, if life arose there, would be supplied by a generous photon flux at near infrared wavelengths where its star emits most abundantly. And it is close enough to Earth, 40 light years, nearby in galactic terms, that the instruments now being built can actually measure its atmospheric composition. Compare TRAPPIST-1e to the other most discussed habitable planet candidates in the scientific literature. Proxima Centauri b is at 4.2 light years, tantalizingly close, but orbits an even more active M-dwarf that produces extreme UV flares, and it has no confirmed atmosphere, no confirmed transit geometry, making atmospheric characterization much harder, and a stellar environment that many researchers consider more hostile than TRAPPIST-1. Kepler 442b orbits a K-dwarf, receives a stellar flux of about 70% of Earth's, and has a radius suggesting it could be rocky. But it's 1,200 light-years away, far beyond any possibility of atmospheric characterization with current or planned technology. LHS 1140b, orbiting at 41 light-years, is a promising target. It transits, it's in the habitable zone of an M-dwarf, and JWST is actively observing it. But early JWST constraints on LHS 1140b's atmosphere are still preliminary, and the system lacks the detailed mass characterization and resonant architecture of TRAPPIST-1. TRAPPIST-1e sits at an intersection that no other candidate occupies, close enough for atmospheric characterization, rocky and well measured enough for interior modeling in a system whose full architectural context is understood, around a star whose longevity is genuinely unmatched, with a water inventory that the density data consistently suggests is substantially richer than Earth's. No other planet we have found combines all of these properties simultaneously. Not any of the Kepler planet candidates around G-dwarfs, most of which are too distant for atmospheric characterization. Not the Alpha Centauri planets, whose host star systems have their own habitability complications. Not Mars, not Venus, not any other candidate in our solar system. TRAPPIST-1e is the specific combination of characteristics that makes the question of superhabitability empirically testable by instruments that exist or are under construction on a planet within observational reach, around a star whose longevity reframes the entire concept of what it means for a world to be a suitable home for life. The concept of superhabitability asks a question that sounds almost impertinent. What if Earth is not the best possible planet? What if the universe contains worlds where life has had more time, more water, more chemical energy, more evolutionary opportunity than it has had here? Worlds where the biosphere, if it ever got started, is not 3.8 billion years old, but 6 or 7 billion years old. Worlds where shallow, warm seas cover 90% of the surface. Worlds where the geological engine driving chemical gradients and atmospheric recycling has been running longer and hotter than Earth's? The answer might be yes, and TRAPPIST-1e is one of the most plausible candidates we've found. Not certainly, not without important caveats. Not immune to the possibility that the early stellar activity stripped everything interesting away, but plausibly, seriously, scientifically, defensibly plausibly. The photograph of a habitable zone planet is coming. The technology is in orbit. The telescopes are being built in Chile. The atmospheric absorption features are in the models, waiting to be matched or not matched by the actual data. The transit of TRAPPIST-1e in front of its crimson trillion-year star happens every 6.1 days, with the patience of a star that has been doing this for billions of years, and will still be doing it long after our own sun has been dark for 1 trillion years. We found it. We're looking at it. We're asking the question. In 10 years, we might have the answer. And if that answer is yes, if JWST accumulates enough transit data to resolve a CO2 absorption feature in TRAPPIST-1e's spectrum, if the ELT follows up with oxygen or ozone, if the infrared vegetation edge appears in the disk-integrated reflectance, then the answer to the question posed in this video's title won't be a hypothesis anymore. It will be the most important empirical result in the history of science.